All right, so in this lesson in section 5.3, we're going to be working with independent events and finding probabilities of independent events and some dependent events. And we're going to be using the multiplication rule to do this. We're also going to use when we see some at least situations. How do we compute those probabilities? Here's some basic definition. Two events, E and F, are independent if the occurrence of one event in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of one event in a probability experiment affects the probability of the other. Usually, I usually pay attention to here with the type of problems where they talk about whether I have replacement, whether I'm taking items out of a bag or a deck of cards, and I key in the word replacement. If we're using the same item multiple times to do multiple events, if we are not replacing it, then it is a dependent situation. If we're changing up objects, going from dice to coins to spinners, then those are independent because one thing doesn't affect the other. But if you happen to be staying with the same type of item, like using a deck of cards or using a bag of marbles, if you're not doing replacement, then you have a dependent situation, which means you have to adjust the second fraction, numerator, denominator sometimes, in order to continue with the multiplication rule. Quick little note here, again, thinking about tossing a coin multiple times. Whether you get heads on the first one doesn't dictate whether you get heads on the second one. Those are independent events. So the multiplication rule says that if I want to find the probability of event E and event happening, I could just, if they're independent, multiply the two together. So what's the probability of getting heads and rolling a 2? Well, that would be just probability of a heads and a 2. Well, since those are independent things, we changed up items. Probability of heads times the probability of a 2, which would be 1/2 times 1/6, which would be 1/12. Yeah, there we go. We can do the same thing with multiple. We're not limited to just doing it with two things. We can do it with a whole bunch of events. We can just keep multiplying each of their individual probabilities together. We have a few examples here. What's the probability that a randomly selected 24-year-old male will survive the year? It's 99.86%. What is the probability that 3 randomly selected 24-year-olds will survive the year? So again, we can take the probability of the first one times the probability of the second one times the probability of the third one. So that would be just taking 0.9986 times itself 3 times. It's not multiplying it by 3. It's timesing it by itself 3 times. Multiplying by 3 would be like if we were adding the probabilities. So when I multiply those out, real quickly, 0.9986 is 0.9958. Those are the first, and then the next one was a 0, so that would just make me be rounded to leave it as an 8. What is the probability that 20 randomly selected 24-year-olds? Well, in this one, again, we could take each one, person 1 times person 2 times person 3, and we can keep going all the way to person number 20, all the way out to person number 20. That takes stinking forever. So what we could do, since they are all the same probability of occurring, what we can do is we can say, you know what? I can actually take it, the 0.9986, and raise it to the 20th power. And then therefore that would give me what the probability would be for that. So 0.9986 raised to the 20th power, and that is 0.9724. It was 97236, so we'll round it to 24. So there's a 97.24% chance that 20 randomly selected 24-year-old males will survive that year. Computing the at-least probabilities. Now this is a situation where we're going to use the complement rule to help us out. The at-least situation can add up. I mean, and that's what we have down here. So same situation with the 24-year-olds, but we have a fixed number of 24-year-olds we're pulling from. So we want to figure out what the probability of at least one male out of 1,000 age 24 will die during the course of that year. If the if the probability that the survival rate is 99.86. So these events are mutually exclusive. So what we can do is we can add up the individual probabilities. What's the probability that one of them dies, or two of them die, or three of them die, or four of them die, or all 1,000? That would be the case of the at least one. So that would be a lot of calculating and then adding up. So the probability of one dying would be like 0.0014. Because if that's my survival, then that probability of dying is 0.0014. So we would have to go through and, the second one, we would add to that 0.0014, two people dying, so that'd be squared. Then doing the same thing for three people dying. Again, I would have to add up all of these answers all the way out to having the last one being 0.0014 raised to the 1,000th power. And so that's just a lot of math. So what we can do when it's at least one, we can do the one minus the probability that nobody dies. So we're going to go one minus. Now, nobody dying, that means that's surviving. So my survival rate is 0.9986. And it's out of those 1,000 people, so 1,000 males. So that will be my exponent. And then now, depending on how fancy your calculator is, kind of dictates whether you can put this in one fell swoop or not. If you have a small calculator, it may not be able to do it. So I'm going to try with my small calculator. 1 minus 0.9986 raised to the 1,000 power. And it gave me 0.7536. And it's technically a 4 after that, but we're going to go ahead and chop it off right there. So there's a 75% chance that at least one male out of those 1,000 is going to die during the course of that year. Okay, at least one. Determine whether the following events are independent or dependent. Again, justify your answers. Event E is speeding on the interstate. Event F is being pulled over by police. Well, if you're speeding on the interstate, then you're probably going to get pulled over by the police. So I would say those are dependent. You gain weight for event E, and the probability and then event F is you eat fast food for dinner every night. I would say those are dependent. Typically, the more fast food we eat, even though it's yummy, it has a tendency to make us gain weight faster. Last one, you get a high score on a statistics exam, and the event F was the Boston Red Sox win a game. Whether you get a high score on your statistics exam, is that going to really influence the outcome of the Red Sox baseball game? No. So we would say those would be independent. All right, so just some more examples of just seeing using the multiplication rule. About 13% of the population is left-handed. If two people are randomly selected, what is the probability that both are left-handed? So what's the probability that I do lefty, lefty? And so on that case, it would be 0.13 times 0.13. There's still an independent situation, since we're working with the proportions there. So that would be 0.0169. Would be what that would be. What is the probability that at least one is right-handed? So probability at least one is a righty. All right, well, now this one's a little bit different. So if we think about doing our sample space here, if I'm picking two, I could have a lefty and a lefty and a righty. I could have picked a righty first and a lefty, or I could have gone righty and righty. So with that in mind, at least one would be these three added up. So we could go through and find out those probabilities of doing like 0.13 times. If you're not a lefty, that means you're a righty. So That would be 0.87. And then we would go 0.87 times 0.13. And then this one would be 0.87 times 0.87. And then I would get those three answers. Get those three answers there. And then add them up. And that would be the probability of at least one. Or we can use the complement rule. We can do the probability 1 minus the probability that they're not righty. They're not righties. So that would mean that they're both lefties. Okay, so that'd be 1 minus probability both lefties. And we already have that there, so we would just go 1 minus 0.0169, and that would be 0.9831. So there's a 98.31% chance that we would choose somebody that is at least one is right-handed. All right, next problem. The probability that a randomly selected 40-year-old male will live to 41 is 99.757, according to the Vital Statistics Report. What is the probability that two randomly selected 40-year-olds live to be 41 years of age? All right, great. So 2, again, we can take 0.9975 and multiply it by itself. We got 2 events there, 99757. And then that gives us, let me get my calculator rocking here. It gives us 0.9952. What is the probability that 5 randomly selected 40-year-olds? Okay, I'm going to use that exponent trick. 0.99757 raised to the 5th power. That gives me 0.9879. Part C, what is the probability that at least one of the 5 will not live? Okay, and then we got a follow-up question. Would it be unusual if at least one of the 5 selected 40-year-olds male did not live? So let's first find this one. What's the probability at least one dies? Because it says not live. Well, at least one does not live. So we can do, instead of doing a big long tree diagram to figure this out, we could do 1 minus the probability that they all live. Oops, they all live. So that would be 1 minus 0.99757 raised to the 5th. That was the last answer we just got there. So 1 minus 0.9879, which would be 0.0121. So there's a 1.21% chance that at least one dies. All right. So would it be unusual if at least one of the 5 randomly selected 40-year-old males did not live? And again, this goes back to our interpretations. Would it be unusual if at least one of the 5? Again, it's a 1% chance. It's slim. It's a slim chance that that'll occur. So I wouldn't say it's too unusual, but it always comes down to, okay, what are we comparing it to? If 5%'s the cutoff, well, 1%'s less than 5%. So yeah, it would be unusual for at least one of them to do, because that is a low percentage. So I could see saying yes, it is unusual, since that's a really low percentage there. I believe this is the last problem in our lesson here. So derivatives in finance. A derivative is a financial asset whose value is determined or derived from a bundle of various assets, such as mortgages. Suppose a randomly selected mortgage has a probability of 1% of default. Okay, what is the probability of a randomly selected mortgage will not default? Well, if the probability that it defaults is equal to 0.01, then the probability that not default is basically the complement. So that would be 1 minus 0.01, which is equal to 0.99. There's a 99% chance it will not, and then therefore pay off. Part B, what is the probability that a bundle of 5 randomly selected mortgages will not default, assuming the likelihood of any one mortgage being paid off is independent of the other? Again, note a derivative might be an investment in which all 5 mortgages not default. Again, probability that will not default. So that would be our 0.99 raised to the 5th power. So 0.99 raised to the 5th is 0.95. It's actually, it is 0.95099, so that would be like 0.951 is what that would end up being. Part C, what is the probability that the derivative becomes worthless? That is at least one of the mortgage defaults. So at least one. So it'd be one of those 5. So we could do 1 minus the probability that none default. So that would be 1 minus 0.951, which is 0.049. And then it says in Part B, we made the assumption that likelihood of default is independent. Do you believe this is reasonable an assumption? Does one investment affect another? That is a big, I guess that's a nice big question to kind of talk about, how much do you know about financial investments, and could one affect another? My knowledge of investments and portfolio kind of things is kind of limited, but we did have the mortgage market did crash years ago with a bunch of different bad loans, and so I would say that they weren't independent. Just from my thinking is I think they're more dependent based on how things are going there, but that would we have to dive in and do a little bit more research on, just if we wanted to be fully informed on it. So